Alright, so in this video I'm going to be explaining another important article with the title Accurate Learning of Graph Representations with Graph Multiset Pooling. This ICLR paper in 2021. Graph neural networks have been widely used in modeling graph data, achieving impressive results on node classification and link prediction tasks. Yet obtaining an accurate representation for a graph further requires a pooling function that maps a set of node representations into a compact form. A simple sum or average over all node representations considers all node features equally without consideration of their task relevance and any structural dependencies among them. Recently proposed hierarchical graph pooling methods, on the other hand, may yield the same representation for two different graphs that are distinguished by the Weiler-Lehmann test, as they suboptimally preserve information from node features. To tackle these limitations of existing graph pooling methods, we first formulate the graph pooling problem as a multiset encoding problem with auxiliary information about the graph structure and propose a graph multiset transformer, which is a multi-headed attention-based global pooling layer that captures the interaction between nodes according to their structural dependencies. We show that GMT satisfies both injectiveness and permutation invariance, such that it is at most as powerful as the WL graph isomorphism test. Moreover, our methods can be easily extended to the previous node clustering approaches for hierarchical graph pooling. So, the concepts on the left, conceptual comparison of graph pooling methods. Gray box indicates the readout layer, which is compatible with our method. Also, green check icon indicates the model that can be as powerful as the WL test. And on the right, you see an illustration of set, multiset, and graph multiset encoding for graph representation. For example, diffpool is a clustering. They cluster nodes, and so each node belongs to one cluster, and we fix the number of clusters in advance, or min-cut pool, which I have explained these two in different videos. So both graph pooling approaches have obvious drawbacks. First, node drop methods unnecessarily drop some nodes at every pooling step, leading to information loss. On the other hand, node clustering methods compute dense cluster assignment with an adjacency matrix. This prevents them from exploiting sparsity in the graph topology, leading to excessively high computational complexity. To obtain accurate representation of graphs, we need the graph pooling function that is as powerful as the WL test in distinguishing two different graphs. Note that a set of nodes in a graph form a multiset, a set that allows possible repeating elements. Therefore, contrary to previous set encoding methods, which mainly consider non-graph problems, we regard the graph representation learning as a multi-set encoding problem. So the preliminaries of GNN is that we have aggregation and then we update. And for pooling, we need a readout, a combination of these representations to have one single graph representation vector. And I've explained different methods for node drops, that they select highest scored nodes I that with learnable scope function S to drop the unnecessary nodes, where function S depends on specific implementation and top K function samples the top K nodes by dropping nodes with low scores, whereas node clustering methods learn a cluster assignment matrix with node features to coarsen the nodes and the adjacency matrix. We now describe the graph multiset transformer, which can accurately represent the entire graph. Given a multiset of node features, we first introduce a multiset encoding scheme that allows to embed two different graphs into distinct embeddings, and then describe the graph multi-head attention that reflects the graph topology in the attention-based multiset encoding. To overcome the inability of simple pooling methods, such as sum on distinguishing important nodes, we use the attention mechanism as the main component in our pooling scheme. Assume we have n node vectors and the input of the attention function consists of query and key and the value, where n sub key is the number of query vectors, n is the number of input nodes, d sub k is the dimensionality of the key vector, and d sub v is the dimensionality of value vector. Then we compute the dot product of the query with all the keys to put more weights on the relevant values, namely nodes that this WQ transpose times value, QK query times key times value, which we use for attention. Then they have this multi-headed variation of this formulation. And while multi-head attention is superior to trivial pooling methods, such as sum or mean, as it considers global dependencies among nodes, the multi-head attention suboptimally generates the key k and the value v, since it linearly projects the obtained node embeddings to further obtain the key and value pairs. So to tackle this limitation, we newly define a novel graph multi-headed attention block. Formally, given node features H with their adjacency information, we construct the key and value using GNNs to explicitly leverage the graph structure like this. So we now propose a graph pooling function that satisfies the injectiveness and permutation invariance such that the overall architecture can be at most as powerful as the WL test. So we define the graph multiset pooling, which is inspired by the transformer to compress the n nodes into k-typical nodes with a parameterized seed matrix S. For the pooling operation that is directly optimized in an end-to-end fashion. And here is the row-wise feed-forward layer that processes each individual row independently. Ln here is a layer normalization. So while previously described GM pool condenses entire nodes into k representative nodes, a major drawback of this scheme is that it does not consider relationship between nodes. To tackle this limitation, one should further consider the interactions among n or condensed n k different nodes. To this end, we propose self-attention function inspired by transformer, where compared to GMH that considers interactions between k vectors and n nodes, self-attention captures interrelationships among n nodes by putting node embeddings H on both query and key locations. So given a graph passed through several message passing layers, We use an attention-based pooling block and a self-attention block to compress the nodes into few important nodes and consider the interaction among them respectively with the multiset framework. So we describe this graph multiset transformer, which consists of GNN and pooling layer using the ingredients that we talked for a graph G with node feature X and adjacency matrix A. So we have this encoder, GNN of GNN. So we can stack several GNNs to construct deep structures. After obtaining a set of node features from an encoder, the pooling layer aggregates features into single vector form. But to deal with a large number of nodes, we first condense the entire graph into k representative nodes with graph multiset pooling, which is also adaptable to the varying size of nodes, and then utilize the interaction among them with self-attention block. Finally, we get the entire graph representation by using GM pool.